So now we're going to start learning the specific models, and we will start with the first model, which is single server. And it's very important to know what are the assumptions underlying this model. Okay, so why this is important? Because if you want to apply the model, for example, for a situation where you believe that one of these assumptions is not true, then you cannot use it. It's very important that you know that. Okay, so here we know that we have a single server, of course, from the name of the model. The arrivals follow a Poisson distribution. The service time follows an exponential distribution. You are following a first come first serve, of course, discipline, and no bulking or renagging. So you can see that really these assumptions are very realistic, right? I may think only about, for example, service time. This may not be true at all times. So before you go ahead and use this model for a certain application, a real application, make sure that you have the data and you observe the distribution so that you know that the service time is really exponential distributed before you start using this model. So with this model, we have the following specific formulas that apply only for this model and not to any other model. First, the probability that the service capacity, the service facility is idle, meaning that no one there are 0 units in the system. Let me say something about that. Remember, we said that who wait in line can be people, can be trucks, can be airplane, can be cars, can be orders. So that's why in many cases we refer to these as units or entities. Now, if we are sure that these are people, we call them customers or persons or whatever. But in general, you can use that units in the system. So these can be anything, right? People, trucks, whatever. So P0, when we have a single server, it's equal to 1 minus, again, this ratio, our famous ratio lambda over mu. Probability of n units in the system where n can be any number above 0, so it can be 1, 2, whatever, any number, it's given like that. It's in fact it's function of P0, so it's equal to the ratio lambda over mu, again this ratio, to the power n, where n is the number of units that we are interested in, and we always multiply by P0. Okay, so if you want to find P2, we substitute that with 2. P3, we substitute with 3, etc. Average number of units waiting for service. So average customers, for example, waiting in line. So this is LQ. LQ is equal to lambda squared divided by mu minus lambda. Here also I need to say something about the condition that we defined before, or that we discussed before, that the models apply only for underloaded system. And remember what we meant by underloaded system, meaning that mu, which is your capacity, should be greater than lambda. Otherwise, you cannot use the model. Now, let's say you did not pay attention to that and you have a situation where mu is less than lambda. So look what happened here. Mu minus lambda, where mu is less than lambda, this will be negative. And your answer here will be negative, which does not make sense, right? Because you are trying to find the average number of people waiting in line. It cannot be negative. So this will give you an indication that there's something wrong.